Hello everyone, my name is Ferhat Özgür Çatak. Today I will present our paper, which is Mitigating Attacks on Artificial Intelligence-Based Spectrum Sensing for Cellular Network Signals. You can access our implementation, our source code using my GitHub repository. This table shows KPI and compares the KPI of 5G and 6G networks. As you can see the table, the KPI values are much higher in 6G. For example, the peak data rate in 5G networks is 20 gigabit per second and it would be 1000 gigabit per second in 6G networks. In order to achieve these KPI indicators, we need to develop different techniques, different methods. The first one is new spectrum usage and radio design paradigms. Also, we need to implement novel network architectures. Another thing is to enhancing network coverage beyond terrestrial domain. And the last one is increasing intelligence and automation, which means that we need to use AI in our implementations. This figure shows the potential applications of AI or artificial intelligence at different layers of wireless systems. You know, a typical wireless system contains different layers. It contains a physical layer and it contains network layer. In physical layer, we can use AI for channel estimation, symbol detection, channel decoding, resource allocation, and scheduling. For the network layer, we can use AI for network planning, orchestration, routing, and network operations, fault analysis, and recovery. The next generation of wireless networks, 5G and beyond, is being designed with the artificial intelligence at its core. This will enable a wide range of new applications and services, including autonomous vehicles, remote surgery, and Internet of Things. However, AI also introduced new security risks, cybersecurity risks, which are magnified in the context of 5G and beyond. In particular, AI algorithms are susceptible to adversarial machine learning attacks, in which an attacker can manipulate the data to fool a target or victim machine learning algorithm into making incorrect decisions. Adversarial machine learning attacks can be used to launch the wide range of attacks on 5G and beyond networks, including denial of service attacks, spoofing attacks, man-in-the-middle attacks. There are 4 different components in our research. The first one is dataset. We generated 5G, LTE, and noise signals using MATLAB toolboxes. Second component is DL model, deep learning model. We used semantic segmentation based deep learning model to build the prediction model. The third component is attacks. Here in this research we used several adversarial machine learning attacks to penetrate the victim deep learning model. As mitigation part, we use defensive distillation based mitigation to protect our deep learning model. I will explain them. In this study, the synthesized dataset is utilized and generated by using 2 MATLAB toolboxes, which are 5G toolbox and LTE toolbox. Then, the generated dataset, including LTE, 5G, and noise signals, is divided into training and testing datasets. Each frame of 40 milliseconds is randomly shifted in the frequency domain. It is assumed that LTE and 5G signals are in the selected band range, and the network performance is evaluated based on distinct random bands. In this example, here there is an example figure. The sampling rate is 61.44 MHz, which is adequate processed LTE 5G signals. Then we created an image which is 256 by 256 spectrogram images. We created these images from complex baseband using baseband signals using an FFT, phase Fourier transform, length of 4096. Then we trained the network with the frames of contain 5G, LTE, and noise signals. Each frame is 40 milliseconds long, and which is the duration of 40 subframes. The network assumes that the 5G, LTE, or the noise signals occupies the same bandwidth, whole frame duration. Another component in our research is semantic segmentation. Semantic segmentation is the process of classifying each pixel in an image into a set of categories. For example, in an image of city space, each pixel could be classified as belonging to a building, road, sidewalk, or a tree. One of the prediction performance metrics in semantic segmentation is intersection over union, IOU. IOU is the ratio of the area of overlap between the predicted segmentation and the ground truth segmentation to the total area of union of two. And the third component in our research, which is adversarial machine learning or hacking AI models. There is another term in deep learning area, which is generative adversarial networks, but they are completely different. GAN is completely different topic. DNN models or deep learning models or AI models are highly vulnerable for the crafty design malicious inputs. DNN models contain many vulnerabilities and weaknesses which make them difficult to defend in the context of adversarial machine learning. For instance, they are often sensitive to small changes in the input data, resulting in unexpected results in the model's final output, model's prediction. Another component in our research is defensive distillation-based mitigation. Defensive distillation is an adversarial training technique that adds flexibility to an algorithm or model classification process so that the model is less susceptible to exploitation. To improve the accuracy in distillation training, one model is trained to forecast the output probabilities of another model trained on an early baseline standard. So it means that there are two models, the teacher model and student model. First we are training the teacher model, then we are training the knowledge from teacher model into the student model. So the robust model here, the robust model is student model. We can deploy the robust student model into the development environment. This is our system model. The proposed approach is implemented in Python programming language. We use CNN-based segmentation model. And this model is based on ResNet 50 and retrain it using dataset using the MATLAB. The RMS probe optimizer is used for the training model. Also, we use cross entropy as the loss function. The model is trained in two phases using the proposed approach. The first one designed to train the base model, and the other one designed to defend the base model against adversarial machine learning attack. The base model is trained with the cross entropy loss function, and the proposed approach is designed to train the distilled network with a loss of combining the cross entropy and Kullback-Leibler divergence, which is called a defensive distillation. The model architecture of the spectrum sensing model, which is shown in the figure, and the second figure on the left side shows one of the example instances from the dataset. As you see, the first figure, figure A, is the received spectrogram. It means the input for the CNN model. The other one, figure B, is the true signal labels, which is the real output of the input. And figure C is the prediction of the CNN-based spectrum sensing model with received spectrogram. And figure D is the confusion matrix of this prediction. For experiments, the second step is to attack this CNN model with FGSM, BEAM, and PGD attacks. We use three different adversarial machine learning attacks: fast gradient sign method, BEAM basic iterative method, and PGD projected gradient descent. The epsilon values, which is the attacker's budget of FGSM, BEAM, and PGD attacks, are selected from 13 to 128. The number of iterations involved in the BEAM and PGD attacks is 2000, because BEAM and PGD attacks are iterative approaches to find the manipulative inputs. These tables together show the prediction performance results of the defended and undefended CNN-based spectrum sensing models against the attack for the three different epsilon values, with the different metrics of LTE, 5G, and noise. According to the tables, the defended CNN model has higher prediction performance when compared to undefended model. Also, IOU metric values of the defended or robust model and the undefended model, which means without mitigation method, are shown in these figures. The x-axis shows the epsilon value of the FGSM, BEAM, and PGD attacks, while y-axis indicates the IOU values of the defended and undefended models. As shown in the figures, the defended model has higher IOU metric values when compared to the undefended model. The trend lines also show in the figures, and the slopes of these trend lines show the undefended model has a lower decrease rate when compared to the undefended model. The first obvious result is that defensive distillation-based mitigation method can significantly reduce the vulnerabilities of AI-based spectrum sensing models against adversarial attacks in cellular networks. And the last two histogram plots of the IOU metric values for each attack of defended and undefended models. For the defended model, the IOU values are clustered around 1, which means that CNN model can correctly recognize LTE, 5G, and noise signals. These are our observations. We have 4 different observations. The first one, the CNN-based spectrum sensing models are vulnerable to adversarial attacks. Observation 2, there is a strong negative correlation between attack power, which is epsilon, and the model prediction performance. Observation 3, the proposed mitigation method offers a better performance against adversarial attacks. And the last one is a defended model has a lower decrease rate when compared to undefended model. Conclusion. We performed a vulnerability analysis for AI-based models for identifying cellular network signals under adversarial attacks. The defensive distillation can defend the CNN-based spectrum sensing models against adversarial machine learning attacks in cellular networks. The CNN-based spectrum sensing model can identify the type of cellular signals, whether LTE, 5G, or noise. The original CNN-based spectrum sensing model is significantly vulnerable to adversarial attacks. Okay, thank you for listening.